All right, so thank you so much for joining us today. My name is Leela Nordman, and I work at the Fairbanks Museum and Planetarium. And today our class is by Michael Simoniello, and he's going to be doing freezing and boiling for us. So it's probably about a 45-minute to an hour-long class, depending on questions. And again, join us at 1 o'clock for additional classes today, and also check our virtual learning web page for additional classes starting again next week. So for those joining us in Zoom, again, feel free to scroll your mouse down and click on the chat button. And that's one way that I can ask questions of Michael for you all. And then also there is the Q&A button, which you can also click on and bring up. So again, asking questions, and I will go ahead and interrupt Michael just to get those questions asked. Unfortunately, on YouTube, we are streaming to it live, but we do not have the chat function enabled currently. So just to let you know that if you would like to email us, you can certainly email Drew Bush, dbush@fairbanksmuseum.org with your questions, and we will try to answer them in real time or at least shortly after the class. So with that, I'm going to go ahead and turn it over to Michael and to freezing and boiling. Thanks so much.
All right. Hello, everybody. Good morning. Welcome to Freezing and Boiling. So in this class here, we're going to be discussing and also doing some demonstrations here, all based on the state or phase changes of water. So we're very familiar, of course, with water as, an essential substance for our own bodies and, for all purposes in our lives. But it's a particularly important substance to study because we interact with it on a daily basis in all three of its material stages or phases or forms, right? Every single element and every single chemical compound can exist in three forms here on Earth, of course. And we know them as liquid, solid, and gas. Water, of course, we know, can take any of these three forms in even in our own home, between liquid form, which of course we call water and we use every day, to ice, its frozen form, and of course water vapor, its gaseous form. You probably interact with each of these three forms once or twice every single day. So it's important to know exactly how they function, how water can transition between liquid to solid to gas. There's already a question? Let's hear it.
Yes, and just asking, what plasma?
Right, so plasma is a superheated state of matter. You might know that the sun is primarily composed of superheated plasma. Plasma does not form naturally anywhere on the surface of the Earth. That said, humans have been able to make it occur. If you've ever heard of like a plasma torch, some welding gear actually superheats gas, usually like argon or xenon gas. So I think it's the same type of stuff that's used in neon lights. Actually, it's superheated to the point where it turns into plasma, and it's used to cut things like metal or other very hard substances. So you can find the state of plasma in some substances on Earth, but not naturally. Liquid, solid, and gas are the three that you could find in a natural state here on planet Earth. But that is a good question. Okay, so, well, as we get started here, I'm just going to light my butane torch. So just as an introduction to the changes in the state of matter, we're going to be working with a little bit of water here, of course, in my heat-proof flask, and I'm going to be lighting this butane torch to boil this water. Now, I'm sure you all know, because we're quite familiar with water, the boiling point of water is only 212 degrees Fahrenheit or 100 degrees Celsius, right? Compared to a lot of materials, this is an extremely low boiling point. there are lots of substances that their boiling point is in the thousands of degrees, right? Temperatures that are, almost impossible to reach naturally on Earth. So water is one that's very easily achieved. But, for instance, if you've ever seen or used or watched a video of liquid nitrogen, nitrogen is a substance that actually boils at about, something like negative 300 Fahrenheit. That's its boiling point. So no matter where you have liquid nitrogen on Earth, even in places like Antarctica or here in Vermont in the wintertime, it will be boiling. In order to make liquid nitrogen, you have to take the nitrogen gas that's in our atmosphere and pressurize it down. So everybody knows that you can change the state of a substance like water by changing its temperature, right? That's what we're doing right now. We're taking this liquid water, which is about 70 degrees, about room temperature, and we're bringing it up to 212 so that it boils. We could similarly make this water in the flask boil if we decrease the pressure in the flask. There's no way for me to do this right now, but if I had some kind of plunger or like a syringe head here attached to this, and I actually lowered the pressure of the jar, I could make this water boil, start to bubble, to turn into water vapor without changing its temperature at all. Similarly, if you take water vapor, water gas, there's plenty of water vapor in this room right now, in your room, in the atmosphere outside, certainly. If you take any of that water vapor and condense it, pressurize it down, it will go from a gas to a liquid. So the two primary ways that you can change the phase of any material is through changing its temperature or by changing its pressure. So just as I was saying that here, my water sample is already starting to boil a little bit. You probably can't see it quite yet from where you are. I might move the computer pretty soon as this begins to go.
We do have a question, and I'm not sure if you know the answer to this, but someone was asking, if you put liquid nitrogen into molten lava, would it make it a liquid, solid, or gas?
If you put liquid nitrogen into molten lava,
I think it would just freeze the lava in place, wouldn't it? I mean, because it's so cold. I think of like how when you release liquid nitrogen, or like you pour it on something or you dip something into it, it freezes everything so solid that you can break it. But I don't know. Yeah. That might be a good research question to look up.
So yeah, so the laws of thermodynamics state that heat always moves from hot bodies to colder bodies. That's how any kind of heat interaction works. If you were to take liquid nitrogen, which is extremely cold, and lava, which is obviously extremely hot, can be into the thousands of degrees, right? If you had those two substances together, the heat from the lava would transfer into the extremely cold liquid nitrogen. And what would happen is it would cause that liquid nitrogen to boil extremely fast, to turn into nitrogen gas faster than it normally does when it boils, extremely fast. And of course, as the heat transfers out of the lava, it's going to cool down, but it probably won't cool down enough for it to solidify. What would probably happen is, for instance, if you have an electric range at home, like one of those flat top ones, and you get it super, super hot, and actually I could probably bring the computer into my kitchen in a minute and show you. But if you take room temperature water and pour it onto a heating coil that's super, super hot, what will happen is that water will instantly try to turn it into water vapor. It'll instantly begin to boil and evaporate. it's pretty cool. And in fact, I will show you that in just a minute. But as for right now, yeah, is it on? Could you put it on high? Oh, super. Okay. Here. My flask here is still taking a moment to boil. I'll just show it to you in the state it's in right now. So just like when you boil water on the stove, you'll notice that the first place that your water vapor is going to start to form will be right at the bottom of your container, right? That, of course, is going to be the hottest part of the entire container because the heat source is coming up from the bottom. And those little bubbles that you see are actually, that is water vapor. So that is water that has gotten just above that 212 degree threshold, and it has turned from liquid to gas. And in that transition from liquid to gas, those water molecules spread apart pretty significantly. And that this happens with any gas, not just water. And it causes that bubble to become much, much, much lighter than the water around it. Even though it's all still water, it's just water vapor now instead of liquid water. It's very light. And that's what causes those bubbles now very quickly to move from the base of the container up to the top. I don't know if you can see the steam coming out of here on your computer, but there certainly is now. You know, steam is our common word for water vapor. But particularly interesting here, as you can see those rolling bubbles going, all of that water vapor at 212 degrees rising up and boiling out, you can actually see that as that steam rises in my flask here, all around the rim of the flask, you'll notice that there's condensation here. There are all of these little water droplets up here at the rim of the flask. And now these weren't here before when we started out. This is all brand new condensation. The reason that this has happened, this is very interesting, is that as this water down here begins to boil, of course, that water vapor is very light and it wants to rise, and it rises straight out of the flask. But as it's rising, a lot of that water vapor will hit the sides of the flask here. Now, the top sides of the flask are quite far away from my heat source down here. The temperature of the flask up here, it's actually cool enough that I can still touch it a little bit. It's well below the boiling point of water. And as a result, when that water vapor, which is a gas, rises up into the flask, it will touch the rim of the flask there, and it will turn back into liquid because the flask itself is cooler than 212 degrees Fahrenheit. Oh, that's great. I actually had another thermometer here. This is just a cooking thermometer. And it shows, I don't know if you can see on your computer, but it's showing me 212.5 degrees Fahrenheit. And this is a fairly accurate thermometer, I know. So that's proof to you that that's how this works. But okay,
Don't
now
put a ton on there because we don't want to crack it.
oh yeah, no, I know. So here we are in my kitchen at home, and this is a very, very hot heater here. Yeah, could you fill that with water for me? Thank you.
We want to splash it on there.
Yeah.
I think we should make a recommendation that kids don't try this at home.
That's a good point.
This is something that Michael's trying at home, and notice he has a parent with him.
Yeah,
Supervision.
it's
support.
true. So
Okay,
this might
ready?
be hard to see. Yeah, there you go.
You can't even stay on there. It evaporates so
Right.
fast. Do that.
There you go.
Oh, yeah, you can really see it.
The burner.
Yes.
Not red.
A lot of that water is evaporating almost instantly, but another thing that's happening that's quite cool, and you know, with parental supervision, I encourage you to try this at home because it is very cool. What will happen is those big droplets of water that are hitting the stovetop there, they actually become like little water like hovercrafts. That water droplet will hit the hot surface and the bottom of the water droplet will boil, and it'll actually create a little water vapor cushion. So that water droplet is actually not on the surface, but it's actually floating a little bit above the hot surface, and it's riding around on this little cushion of air. It's a very cool thing to see. So again, if you took liquid nitrogen and you poured it on boiling lava, that kind of result is what you would get. The liquid nitrogen would skitter all over the place. It would boil very, very quickly, and it would cool down the lava a little bit, but not enough to turn it solid.
And I think we have a question. It's just why, when I touch a pot, I guess of boiling water, does it not burn me? But I would think, wait, but it will when you don't have the pot. So I think he's saying sort of like maybe when you're touching the top, it's not burning you, but obviously if you touch the bottom, it's going to burn you right away. So I think it's just that level of temperature change, right?
Yes. Mm-hmm. Yeah, that's right. Eventually, if you leave a pot on the stove long enough, or if I leave this flask on the heat long enough, eventually the entire flask will get to the same temperature. But that'll take a little while because the heat will transfer slowly through that material. This is a conversation about specific heat capacity. Different materials have what we call different specific heat capacity, which is basically the time it takes for that material to heat up or cool down. So, for instance, metal has a very low specific heat capacity, particularly stuff like tinfoil. So if you've ever used tinfoil in cooking, you'll know that it heats up super, super fast, like almost immediately when you introduce it to heat. But as soon as you take tinfoil out of the oven, almost instantly it becomes room temperature again because it has a low specific heat capacity, meaning that it heats up super fast and cools down super fast. So that's true of most metals, but water has a very high specific heat capacity. That's why it takes water so long to boil when you have a lot of it. But at the same time, because water takes so long to boil, it also takes a really long time to cool down too. So that's why water, after I boil this water, if I shut off the heat, this water will stay hot for a long time, much longer than the glass flask will. That's a little introduction to specific heat capacity. There's a lot more to learn about that topic. And this is something that you should not do at home. But if you ever have a boiling container like this, and you have a stopper, this is a little rubber stopper, that will completely seal that container, you could cause, an interesting interaction with water or any substance that becomes a gas. So remember, I was saying before that as this liquid water becomes a gas, as it boils, the water molecules separate and split apart, and they basically create a lot of room between one another. And as a result, they get lighter, but also as a result, they take up more space. The same mass of water vapor as any given mass of liquid water will take up much, much more volume. Another way of saying that is that water vapor is lighter than liquid water, but as a result of this fact, if I cap that might be too tight. If I cap my boiling flask here, what's going to happen? So, of course, it's going to build up. There it goes. I didn't touch it. It might have looked like I did, but I didn't. So, as that water boils out into vapor, it's going to expand and expand and expand, and it's going to actually increase the pressure in my jar here.
And we do have a question as to why won't the pot melt, or why doesn't the glass melt?
So I would have to make it. Oh, what is I don't know what the melting point of glass is, but I'm sure that you've seen it. If you've ever seen a video of a glass blower, or you've gone to a glass blower shop, what they do is they heat that glass until it
basically gets to its boiling point and melts and becomes kind of like a half liquid until it's molten, right? 1500 degrees, my dad.
Yep, yeah, that's what I just looked up. 14 to 1600. So yeah, it completely liquefies.
Yeah. This flame here is not nearly hot enough to do that. Oh, I won't do that again. You all got a pretty good image of that just a moment ago. The very last thing that I'm going to use my boiling water for here now is just a little demonstration of how the water cycle works on Earth. This is a very sped up demonstration of the water cycle. But what I have here is a metal pie plate filled with ice, right? And what this represents is the Earth's high atmosphere. You guys probably know that the higher up you get in the Earth's atmosphere, the closer you get to outer space, and the colder it is up there. So I'm going to hold it above the boiling water down here. Now, my boiling water is going to represent water that's all over the surface of the Earth. Think of all of our lakes and oceans, streams, everything, even plants. We'll talk about that in a little bit, but plants and animals are shedding water vapor all the time. And we're contributing to this. This is very sped up, of course. Our oceans and lakes don't boil, but they do pretty much the same thing. Some of the water that's on our Earth evaporates slowly over time, turns into water vapor, water gas, and floats up into the atmosphere, which is what it's doing here. And as it's floating up into the atmosphere, eventually, it'll float up into the high atmosphere where it's very cold. So, of course, once this water vapor gets up here, it's certainly going to be below 212 degrees Fahrenheit or 100 degrees Celsius. And slowly but surely, that water vapor is going to turn back into liquid water. And we call this condensation in the atmosphere. So now, again, you might not be able to see this super well, but if you look at the bottom of this pie plate here, now it's all covered in water droplets. And now you might think, well, those water droplets must have come from the cold ice that's on top of this pie plate. And that's a common thing that people think, but actually all of the water that's all over the bottom of the pie plate here, that's all water from my evaporating flask. That's all water vapor that pretty much turns invisible as it becomes a gas, moves up, hits the bottom of this pie plate, which is very cold, and pretty much instantly it turns from gas, water gas, back into liquid water. And then, of course, what do we know comes out of the high atmosphere is rain, of course. That's where condensation forms up here in the clouds where it's colder. And then as this cloud gets saturated, as lots of water condenses at the bottom of this cloud, it's going to fall back down in the form of rain. And now I would have to wait a little while for that to happen. But that is exactly what will happen eventually. This water will drip down off of the plate back into my flask where it will boil again and evaporate again and reach back up to my pie plate again. So it's a cycle, right? It's the same, I spilled my water. It's all the same water that boils down here, evaporates up to the pie plate here, condenses back into liquid water, and then falls back down into the flask. So you may have heard that all of the water that we have on Earth today is all the same water that we've had for millions and millions of years that the Earth has been around, right? When we change the phase or state of water, like we are here going from liquid to gas to solid ice, we are not losing any water. Even though that water is transforming, it's the exact same amount of water in every different phase. No mass, no weight is ever lost. So that's why in the water cycle, it's the exact same water that we're drinking today that dinosaurs were drinking millions of years ago, right?
because the same water molecules, the same essential components, the elements, have been cycling on our Earth for all of those millions of years. It's impossible to destroy any matter, right? So it's impossible to destroy this water that we're changing the phase of here. Okay, let's shut this off for now. And of course, remember how we were talking about water's high specific heat capacity? That water will continue boiling for 30 seconds after I take the flame away, because water is very, very good at holding heat energy. Okay. This is all very, very hot now. I'll keep it here so that I don't burn a hole in my table. And give me just a minute here to get rid of my ice. Okay, let me take off my oven mitts. So what I would like to show you guys now is a bit of a more complex diagram or example of the water cycle here on Earth. Let's try to share my screen here. Give me just a moment. Okay, excellent. So here is a diagram from the United States Geological Survey Service, showing exactly how our water cycle works. And you can already tell just by looking at all of these arrows here that it's a little bit more complex than what I was just showing to you. But if you look at the right side of the picture where our oceans are, you can see that large arrow rising up off of the oceans into the atmosphere. That is our evaporation, right? It's just like the water that we were just boiling here and causing to rise as gas, right? But like I was saying, we don't see our oceans actually boil, of course. Our oceans and lakes don't get nearly hot enough to really ever boil like that. So how does the water, that liquid water, turn into gas, water vapor? And there's a couple reasons why this happens naturally, but the biggest one is the sun. The sun doesn't give off enough heat energy to the Earth to make the oceans boil, but it does give off just enough energy, heat energy, light energy, to make the molecules of water just at the very surface of the ocean excited, to energize those molecules. What happens when you energize a molecule is you basically make it wiggle faster, you make it move faster. All molecules, the molecules that make up our body, even the molecules that make up a rock or a piece of iron that look like they're still, are really, if you look at them with an extremely strong microscope, they're actually all moving, they're wiggling very, very fast. When you heat up or energize any of these molecules, they will start to move faster and faster. If you cool them off, they will move slower and slower. What happens in evaporation is that the sun energizes the water molecules at the surface of the ocean, and they start to move faster and faster, and they'll actually move fast enough that they will shake themselves free of the ocean. They actually shake themselves off of the surface of the ocean, and they float up into the air as a molecule of water vapor, and then they'll get caught up in this cycle of the water cycle. This is actually helped by wind. You may know that there can be very strong winds over the ocean, and the winds are actually strong enough to rip off individual water molecules off of the surface of the ocean and carry them up into the atmosphere. If you've ever been to the ocean, you've probably experienced this in the form of saltwater spray, right? When it's a very, very windy day, you can actually see that those small you can't see the actual molecules, but you'll see the mists of water that get ripped off of the surface of the ocean and carried up into the atmosphere. So the oceans aren't the only thing that contribute to this, but also I mentioned plants and animals. You know that when you sweat, of course, when your body uses a lot of energy and you heat up, you release quite a bit of water in the form of sweat. But your body is releasing water vapor all the time. Water is evaporating off of your body constantly. And it's the same thing with plants. And in fact, plants do it in a very interesting way. On the underside of plant leaves, they actually have a special kind of organ, a microscopic organ called the stomata. And they actually look like little tiny mouths. And they actually literally are part of the plant's respiratory system. So they are breathing out water vapor and also oxygen. You know that plants exhale oxygen. We inhale oxygen and exhale carbon dioxide. Plants inhale carbon dioxide, exhale oxygen. But just like our breath is filled with water vapor, our breath is wet, plants actually breathe wet water vapor breath also. And when we breathe out, or when plants breathe out, all of that water vapor also rises up in the atmosphere, and it helps to form the clouds. It's interesting to think that the clouds that are above us today are formed partially out of our own breath and the breath of countless plants and animals across the planet. And as we showed with that plate full of ice there, clouds are high up in the atmosphere. It causes all of that water vapor to condense back into liquid water. And eventually that liquid water gets heavy enough and condenses close to itself enough that those slowly condensing water droplets form rain droplets and fall back down to the earth in the form of precipitation, right? And then when that water gets to the earth, it'll run off directly into rivers, streams, lakes, or it will percolate down into the ground. If any of you guys have wells, the water that you're drinking from your well is actually relatively recent rainwater that has fallen out of the sky, percolated into the ground, just like how water percolates through coffee grounds in a coffee maker. That rainwater will seep through the ground, and as it seeps through the ground, it actually gets filtered by all of the soil itself, but also all of the organisms and plant life in the soil, filters out the impurities in that water so that it's relatively clean. And then even underground, that water will slowly flow downhill, just like we see above ground rivers flowing downhill. And your wells basically tap that deep, slowly flowing underground filtered water. And that's what you're bringing up to drink. So that's also fascinating, I think, to me, to think that the water that you're drinking out of your taps every day, if you have a well, was water that was, relatively recently up in a cloud that could have traveled hundreds of miles. That cloud could have begun condensing, somewhere over the Midwest or something like that, and slowly traveled a long distance to be released here in New England. So, is there a question, Leela? Did you just raise your hand?
No, there's not a recent one. Someone was asking about why do things, decompose underground, and I was sort of relating it to the fact that you're talking about the water cycle. There's also sort of a nutrient cycle, and that anything that's sort of breaking down underground is actually just being recycled and being drawn back up by plant roots and tree roots. So
right, yeah,
sharing that out.
You guys probably know that groundwater particularly has lots of vitamins, nutrients, and minerals in it that are important, that are really essential for our body. And the reason why that water has all of those nutrients and minerals in it is because of how that water percolates down through the soil. As that water falls as rain, hits the ground, and then seeps into the soil, it picks up all of those nutrients from decomposing plants and animals, and all of the minerals from the broken up rock matter that's in the soil. And then we drink that, all of that stuff that the water picked up in this cycle. So this water cycle really is one of the most important natural phenomena for human life. If this cycle was interrupted or stopped in any way, really all life on Earth, not only human life, would pretty quickly would be in trouble. So, okay, I'm gonna stop sharing my screen here. Go back to me for a moment. So we just have a couple more things to show you guys today. This might be a little bit of a shorter class because has these demonstrations in it. But I would like to try to show you with my camera setup here. It might be difficult, but I'd like to try to show you how convection works in liquid and also in the atmosphere. Because that whole water cycle that we just looked at is driven by this thermodynamic force that we call convection. The word thermodynamic literally just means the movement of heat, how heat moves. Thermo, heat, dynamic, the movement or mechanics of something. Convection is the process of how heat moves in a liquid or in the atmosphere. You guys have all heard the adage, the saying that heat rises, right? And that's perfectly true. And that's also the main idea of convection. So convection is something that you guys all really have an understanding of already if you understand the idea that heat rises. So I've given a little bit of time for my flask to cool down here. I'm going to get rid of the still warm water that's in here and fill it with cool water, and then I'll come back and we're going to heat up this water again. So just give me one moment. Okay, so I'm back with my flask, and it's filled with at least 3 times more water this time. It's up to about this level. And also this water is relatively cold. I got it out of my tap here. And what I'm going to do is add some food coloring to it. Convection is a thermodynamic force that's happening all around us, but we can't exactly see it because air is invisible to us, and it's very hard to tell when water is moving, right? Under the surface anyway. So what I'm going to be doing is adding a little bit of food coloring to my flask here. And I'm sure you just noticed that as I put my food coloring in here, those droplets all pretty immediately sank right to the bottom. And that's because this water in here is already a little bit warm, and my food coloring is relatively cool. So of course, colder water in a jar full of warmer water here is going to sink to the bottom. If heat rises, cold things must sink, right? So that food coloring sank. But what I'm going to do again is turn on my Bunsen burner here and reheat that water. And as this happens, of course, as we discussed earlier, the first part of our flask here that's going to heat back up is going to be the bottom, where all of that food coloring has settled. I bet that you can already predict. Oh, whoa, that was interesting. Put out my. I bet that you can already predict that as we heat up this water here, that red food coloring that has all sank to the bottom of the glass is going to start to rise up to the top of the glass. So I'll move my camera a little bit here to give you guys a better view. And you can tell that there's more red food coloring at the bottom of the glass than there is at the top here. But you can hopefully already see slowly what's happening to that food coloring there. The dark food coloring is beginning to rise in the glass, and in fact, maybe this will make it even clearer if I introduce a second color. So that green is sinking, but fairly soon as that green food coloring gets down to the bottom of the glass where that's starting to be warm, the green color rises back up to the top of the glass. And so this is the basic idea of convection, or that basic idea of heat rising, hot things rising and cold things sinking. But now the important thing about convection here, and this is exactly what's happening in our atmosphere or in our oceans, is that the hot material down here at the bottom, close to the surface of the Earth, which is the hottest part of our atmosphere, is warming up and rising up to the higher parts of our atmosphere, or the higher parts of the flask, which is cooler, of course. But once it gets up here, it's going to cool back down because the heat is being applied to the bottom and not to the top. So as that material gets hot and rises to the top of the flask, it's going to get up to the top and then cool back down. And then, of course, it's going to fall again. It's going to get pushed back down by the hot material, the hot water that's rising. And it's also going to fall naturally because it's cooling down. So it creates, again, like the water cycle, it's a kind of cycle of movement here, where material gets heated up, rises, cools down as it rises up to a cooler part of the atmosphere, and then it'll get pushed back down and sink back down to the bottom of the atmosphere, where it gets heated up again and moves back to the top. And it creates these convection cycles, which are always moving. You can do this same experiment at home, and it'll probably be easier for you to see than through the camera here, what I just did. If you make a cup of coffee, hot coffee, and then take cold milk out of the fridge and pour your milk into the coffee, you'll be able to see these convection cells. You'll be able to see how the cold milk immediately sinks to the bottom of the coffee cup and then gets heated up by the hot coffee, and then you'll see the milk billow back up to the surface. That's a really great way to see this that you could do just in your own home. But this process, this force of convection, is what creates most wind and local weather in your area. Convection is always happening in the atmosphere, and those cells of moving air, that is literally the wind. As the sun heats up the earth and the air starts to move, moving air, you know what that is, it's wind, right? And this also causes our weather. It's what causes thunderstorms and things like that. This convection.
So we do have, it's a few questions. Like one was, why didn't the water just turn green instantly? And then a second one related is, why doesn't ice sink if it's colder than water?
Oh, yeah, that's okay. So
two very different questions, but
those are both good questions. Yeah. So generally speaking, if I had, let's think. So if I had food coloring and water that was exactly the same temperature, if they were both 70 degrees, and I dropped the food coloring into the water, then the food coloring would start to spread out pretty much instantly because it's all the same temperature. But since my food coloring was cold, because I had been keeping it in the fridge, because the food coloring was cold and the water was warm, the food coloring immediately wanted to sink straight to the bottom of the flask. And only once that food coloring started to warm up will it start to spread back out through the whole flask. If you have food coloring at home and a clear jar of anything, you can do this same experiment in your home and try to see how it works. And the second question, which is a really tricky question, is how come ice floats how come ice floats, basically? So because of the way that ice forms when when liquid water freezes. Liquid water is basically a bunch of water molecules that are all stuck together in a liquid, right? But when you freeze, and they're all kind of they're all jumbled together, they're all stuck together any which way. But when you start to freeze something, all of those molecules, they have to connect up to one another in a very specific way. And that's why with water, we get water crystals or ice crystals. Snowflakes, for instance, are a great example of an ice crystal. They form in a very specific way at specific temperatures. And that's because water, when it's liquid, it'll stick together whatever way it wants. But when you start to freeze it, water will only stick together in 6-sided hexagon crystal structures. Pretty much all materials, as they solidify, will stick together in particular crystal structures. Like metals will do that. All minerals will do that. That's how you get crystals and things like that. But as those crystals form in ice, it actually leaves a lot of air pockets in between all of the crystals. So in a chunk of ice, it's not just solid frozen water, but there is actually a lot of trapped air in there. It's porous. You could think about it like that. And because there's all of this trapped air inside of that chunk of ice, it makes it very buoyant, right? Buoyancy, your ability to float in any liquid substance, is based on surface area, how big the object is, how wide it is, how tall it is. But it's also based on how much air is trapped inside of that object. That's why styrofoam floats so well, but metal sinks. Styrofoam has a lot of trapped air. Metal has very little trapped air. So that's why ice floats. That's also why ice expands. I'm sure you've heard of that too. Whenever you freeze water, any given volume of water, it's going to expand a little bit when you turn it into ice because there's now all that air trapped between those crystals. Is there another question?
So another question is, what does plasma do to gas, liquid, or solid? Is it, I think of it as burning things up, but.
Yeah. Plasma is a hard thing to explain, mostly because it's hard to have an example of it, right? But plasma is basically superheated gas. So like gas, it's individual floating molecules that expand and take up three-dimensional space. So it's not like liquid and it's not like a solid. It's most like a gas, but it's not even a gas because it's so hot. And the thing that separates plasma from other phases of matter is that it's actually its shape and movement is determined by electromagnetic fields. So it's a substance. This isn't the right way to say it. It's kind of like a magnetized substance. If you look at the surface of the sun, if you look at pictures or videos of the surface of the sun, you'll notice that it's all moving, all of that plasma that makes up the corona of the sun. It's all moving, and it's moving in specific patterns. They look like rivers or swirling oceans. And those patterns are actually formed by electromagnetic fields. So that's kind of complicated, and I don't really understand it perfectly at all. But you can certainly read about how plasma works. There's great resources on the internet all about plasma mechanics. That's not something that I know a lot about. Yeah.
And this one might be a little harder to answer. Why do some things mix but other things don't?
Yeah, that's all the mechanics of solution, right? If you take sugar or salt and you pour it into water and you mix it up, that sugar or salt will looks like it disappears, right? It goes into solution with the water, or it dissolves, right? But you know that if you take too much salt or sugar and pour it into a glass of water, you can't make it all dissolve. You can't stir it all in, because there's only a certain amount of any specific substance that you can dissolve in any other substance. Water is a very good solute, which means it's good at dissolving stuff. But think about, for instance, like oil, like vegetable oil is not a good solvent. It doesn't like to dissolve things or incorporate them. So if you make salad dressing, for instance, you'll notice how oil will float above whatever else is in the salad dressing. It won't pick up any of the other stuff because it doesn't want to dissolve any of that stuff. And also it's less dense than water or vinegar or whatever else. So it's going to rise up and float to the top, and it doesn't like to stay mixed. You'll know you can shake salad dressing to get it to mix, but after a few minutes, it'll all separate again. That's kind of a whole different ball of wax, but it's a very interesting subject. It's certainly something that you could spend some time looking up.
And another question is, why does oil light on fire, but water won't? I think it's all about,
that was a great question, because that's pretty much exactly what I'm about to do for the last time here. But you guys probably know that certain elements or certain compounds, mixtures of elements, are flammable, and other ones aren't. That basically means that they react violently to heat. They have a chemical reaction when exposed to heat. So gasoline, for instance, that's in your car, as gasoline evaporates super fast, much faster than water. That gas that evaporates off of the liquid gasoline is super flammable. When you introduce a source of heat to it, like in your engine, that's a spark from a spark plug, it causes a violent chemical explosion, fire, basically, right? Water is not flammable, which means that it does not react with heat chemically. But interestingly, you guys know that, I should have actually said this at the beginning, of course, but water, the chemical formula for water is H2O, right? You've all heard that before, which means that a water molecule is made up of 2 hydrogen atoms and 1 oxygen atom, right? So H2, 2 hydrogen atoms, 1 oxygen atom. And that setup, it kind of looks like Mickey Mouse, 2 hydrogen years and then 1 big oxygen face. That molecule is not flammable, but if you separate a water molecule into hydrogens and oxygen, hydrogen is one of the most reactive elements out there. It's one of the most explosive elements. If you have pure hydrogen and you introduce heat or flame to it, it explodes really violently. If you've ever heard of the Hindenburg disaster, where there was a big Zeppelin that exploded in the early 1900s, that was because that Zeppelin was filled with hydrogen, and it exploded really badly. Also, oxygen also reacts violently with heat. It also explodes or causes fire. But when you put those together in the form of water, they don't react. So it's interesting how elements work like that. Sometimes some of the most dangerous elements out there, if you put them together in a certain way, they become not dangerous anymore. Or on the other hand, if you take 2 elements that are relatively safe for humans and put them together, you might accidentally come up with something that's super dangerous. So, but what we'll be using right now, because again, we can't burn water. You can't use water to cause a thermal reaction. We're going to use a little bit of denatured alcohol fuel. Of course, I'm sure you guys know that alcohol is something that reacts with heat. And the reason that I'm going to be showing you guys this is, for the whole class, we've talked about phase changes in the state of matter of water. And if you remember from the beginning, I said that whenever you change water between a liquid, solid, or gas, you're not removing any of the water. When you take water and boil it into a gas, you have exactly the same weight of gas as you had weight of water. Or if you take water and freeze it and then thaw it, it'll be the exact same weight all the time. But whenever you make a chemical reaction, which is what we're about to do here, you're going to lose some of your mass. When we set this alcohol on fire, we're going to create a chemical reaction. this whole time beforehand when we were working with the water, we were only doing state change reactions. So it's a totally different type of thing. So I don't know if you can tell. Oh, yeah, you certainly can tell right now. But my whole pie plate is now a flame. Hopefully my mom doesn't come in and see what I'm doing. But but what I'm doing right now is and hopefully I don't set off the smoke alarm. But what I'm doing right now is I have caused a chemical reaction to go on with this alcohol here. I am changing the alcohol. If I had this burning pie plate on a scale right now, I would be able to see that this burning pie plate is steadily getting lighter and lighter and lighter. I never remember the chemical formula for this alcohol fuel. I don't think it says. No, it doesn't. I'll have to look it up for next time. But anyway, remember we were just talking about the chemical formula for water is H2O. And there's two H's and one O stuck together. And when you change it from liquid to solid to gas, it's always two H's and one O stuck together. But what I'm doing right now is that I'm changing the actual chemical structure of that alcohol by burning it. I'm splitting it apart. It's going from alcohol to a totally different substance. It's changing chemically. It's not changing its state or phase like we were doing with the water, but we're actually changing its basic chemistry. We're changing its molecules around at the most basic level.
So I have a couple of questions that are from a little bit earlier, but someone was asking, do stars have plasma? And I think you answered that by saying, our own sun or star has plasma. So many of them will have plasma as well. Another question is, if there's a small explosion in a car, then how is the energy contained? And I think of that as like the engine block and the pistons, it's pushing something, but it's very well contained in that metal that won't change matter or has a much higher burning point. So it's very well contained in a car. And then the last one is, why does evaporation go up when gravity is pulling it down?
Okay, that is a good question. So gravity, of course, is pulling down on every single thing on the Earth, right? All being pulled down towards the center of the Earth. And the way that you have to think about this is water doesn't, when it's a liquid water, it doesn't start floating up into the sky because it is, what's the best way of thinking about this? It
like
is
gas, maybe.
Yeah. It's heavy.
Because in the gas form, it's so spread out, becomes much lighter.
Yeah, and the reason that most gases will start to float up is because they're so light and they're so rare that they are. It's so hard to think about how to say it. This is the wrong kind of way to think about it, but they're stronger than the force of gravity. They're think about this. They're so light that the force of gravity isn't strong enough to keep them pushed down. And they're also lighter than everything around them. So certain gases are heavy gases, right? And so they tend to get pushed down by gravity and fall. But water vapor is a light gas, which means that the force of gravity can't keep it all pushed down, and it'll float up and up and up and up until it starts to condense again and turn back into water, which means that all of those molecules start to group up again and become, one big heavy mass, and then gravity pushes it back down again, which is rain, right? Rain is what happens when water vapor can't fight against gravity anymore, and as it condenses and then it falls back down, right? That wasn't a very good answer. I'm sorry about that. I was having trouble figuring out how to word what I was saying.
And I think it's a great question to pose and for people to also do their own research on, certainly. And then there was one last comment, and I don't know if you've ever seen this TV show, but have you ever seen Twin Peaks?
No.
No, yeah. So someone was commenting that you look like a character named Bobby Briggs from it. So yeah, you have to look it up. But that was one of the last comments we had here. So just wanted to share that. But it looks like you've answered all the questions here, and really appreciate it. It looks like we're just at 12 now. So I really appreciate all your energy and time in putting this class together, and answering all those great questions that we had. And again, for folks, will be another class. It's behind or from inside the Fairbanks Museum at 1 p.m. And then again, next week, starting at 9:05, we'll have classes. So thanks again, Michael, and everyone take care.